Hello everybody, welcome to our afternoon talk. It's my pleasure to announce my colleague, Mathias Burger. I will tell you 1 minute about him and then step off so you can finally listen to him. So Mathias has done his study of school and also computer science here in Bavaria. And right afterwards he decided to just stay and move straight on to TNG, which was probably a good decision. And he has had many stops during his lifetime in different parts where he developed software all over the place. Already it started during study. I saw many stops there, and in TNG it didn't stop. He built systems of AI in defect detection for airplanes, in biometrical identification systems, in question answering on medical texts. And that has been so successful that by now he has actually become a full-time intern at TNG. His position is head of AI, and he's been doing that for 3 months now, where he's coordinating all different AI initiatives that we have internally in our company. For example, I'm using his product daily, which is sort of an interface to a lot of different large language models. And I think I'm probably one of 850 in our company that uses it. Exactly. So we have a lot of talks today, a lot of talks about AI too, and many of them are pretty theoretical, but it's very nice for me personally to listen to somebody talk that has actually done it quite a few times. And so I hope you enjoy it, and I will give it up to Mathias for AI Unveiled.
So welcome everybody, and congratulations, you're listening to 3 talks in 1. As the topic states already. So we might be jumping between a few topics because I want to present something state-of-the-art today, and there are quite some things to present. By the way, the slides do not appear. Okay, so we'll talk about AI in a nutshell, then the state-of-the-art, some business potential where you can be inspired and think of what you can do in your company, and then we'll have a glimpse into the future of AI and have a look into the crystal ball. Telling you the bright side of life and maybe also why it might take some years until we get there. So in a nutshell, artificial intelligence systems, it's just a piece of technology that enables machines to act humanly or think humanly. So one of the definitions by Russell and Norvig, a modern approach to AI, is that there are these areas. So thinking humanly focuses more or less on the thought process itself, how we humans do it. Acting humanly focuses more on the acting outcome. It might neglect the thinking part. If a system can just observe and do something that is human-like, that's okay. And then on the other hand, you've got the rationalist approach. So being all logical, having symbolic AI, deducting things, knowledge, and acting rationally as pursuing a goal and maximize the value of your goal. So, there is one area in AI that is very prevalent these days. It's generative AI, and it spans multiple different areas because we have seen multimodal models also. So generative AI may span vision, audition, text, understanding and generation, as well as in some parts also robotic control, because when you've got this brain of the robot that receives user inputs, an LLM, for instance, could lay out the tasks to be performed by the robotic SDK later on. And then let's not forget about other applications in AI. There are still things in understanding like anomaly detections, clusterings, or in forecasting, also things like churn prediction. Why do people unsubscribe maybe from a service? Demand prediction. So that's still there and constantly improving. So please do not neglect that. So to begin with state-of-the-art, I want to present a bit about reinforcement learning. Reinforcement learning means that you've got an agent that knows nothing, like Jon Snow from Game of Thrones, basically. It has some sort of actions and can observe the environment. And when it takes an action randomly, the environment is manipulated, kind of, and then it might get a reward. In the case of robots, it might be just standing upright. So if the robot falls off the stairs, it gets negative reward. And it will try to prevent that. So reinforcement learning agents can be of multiple architectures. So there might be one single central instance where all the observations of the agents are shared. And this central intelligence can also impose policy upon agents. So you might use that in military applications, for example, for unmanned aerial vehicles. Then there's the decentralized setting, which is more cooperative. So the agents can talk to each other. So by network communications, let's imagine shortly that we want to have autonomous cars and they want to optimize traffic flow. So they will communicate with each other or tell the others that there is now a traffic sign that reads 50 instead of 70 and it was not yet on the map. And there's also the fully decentralized setting that's more in the competitive domain. So when you think of playing games like tennis or more in the area of computer games, then you have these settings. And also you can have a mixture. Of course, if you're playing soccer, for instance, you've got two teams. The team collaborates, but they're competitive against each other. Well, so these days, large language models are very prevalent. So basically, there are also agents which can perform some kind of work. And the foundation for performing actions is actually tool calling. So you describe a set of tools that they have at their disposal, like web search, for instance, or writing down files, memorize things, there's a memory aspect. And they can also do some planning, such as laying out tasks to be executed later. So what we see here is from a paper that describes the REACT approach. Whenever the agent receives a question, it starts thinking about it, then it derives an action, like a web search, and it performs an observation. And then the process repeats until a final conclusion is reached. In this case, there's some kind of Apple remote being used, and you want to know how else you can interact with the system. And the first thing the agent does is it thinks about having to search, calls the search action, and finds out that the remote is there to control the front row media center. But how can we interact with it? So the second thought is we have some initial information, but we need to do further investigation into this front row media center thing. So it calls the search again, gets some result, and has learned that you can also use the keyboard instead of the Apple remote control, and reaches the final conclusion and stops there. So there are many kinds of different designs for agents. So one simple one is the plan and execute agent. It follows a certain flow of tasks. So it will firstly plan all the tasks into a task list. Then an agent, it can be a specialized agent for special tasks, will work on those, gather the results, and at the final stage, it will design whether it will find out whether it has to replan or a final conclusion is already reached. If it has to replan, some other tasks are appended to the list, will be performed, executed until the final conclusion is there. Okay, so one of the approaches that is very interesting is flow engineering. So these days, artifacts like LangGraph evolved because you have a certain flow of things, standard operating procedures, so to say. So in the Alpha Codium paper, we see that there are to solve some coding tasks, you should follow certain steps sequentially, and then there are iterations on like writing code until it is executable, writing tests until they can be executed and match the code actually. So other domains are also be brought into this LLM area. You might know Monte Carlo tree search because that is the algorithm that has solved chess and even the Go game. So people also borrow from that. And the basic idea is that there is more than one thought you can have and more than one chain of thoughts that can bring you to a final conclusion that is actually valid. And there might be some invalid ones. So you select a node, a decision, and expand on it. There's a certain action space you can take. You value things. Valuation means that you want to estimate how far you get to achieve your goal. So measuring progress, in fact. And then you simulate that out until you reach the final output, the conclusion. Then you've got this chain of values, and the final output may be reflected upon. So if one thinks that this result is not valid, a very low score is assigned, and those values back propagate through the tree upwards. And then you can say whether a certain decision, early stage, is more likely to have a succeeding result or not. And the tree search mechanism balances a bit between exploration, that means finding new ways of solving things, and exploitation, so taking more likely paths. Let's see how this works out in practice. So on the left side, we see the thought process of an agent. And the thing you should keep in mind is that this Wikipedia search won't work because there's an extra word appended and you just won't find a page for it. So the agent tree search would do that, would arrive at the final conclusion, I cannot find anything, the value is very low, and it will also take that information onto some kind of memory, so the next run of the agent will have this information and might not make the same mistake again. So we take the other path, the thought is slightly different, but the action is the search without this appended word, and that actually succeeds in this case. Well, we can see how that plays out. It plays out pretty well. Let's see the less strong GPT-3.5 model. Their scores on human eval, which is a data set where you have to solve programming tasks, is quite low. But with the agent tree search approach, you can really push it up to nearly double the score. So on the other hand, you also see that GPT-4, being much more strong, better condition on coding tasks, achieves a similar result already. But with the agent tree search approach, or even with just reflecting on your output, you can achieve even higher scores. So you need to ask yourself on how you balance your computational budget, because also as humans, the first thought is not always the one that brings us to the final result. Okay, so there can be more than one agent, of course. You know, we are software developers, there are big companies, and there are different roles. Let's take the very modern approach of the waterfall, because it's easier in terms of communicating. So there are roles like product manager, they will derive the requirements document, for instance, then the architect will create some system design, and the project manager might assign certain tasks to the engineer to be developed, and the QA will check that for whether it suits the use case that was specified beforehand. So the architecture in total looks a bit complicated, but the basic idea is that you have some central message bus. Let's say for you this is Outlook or Thunderbird. Those agents can communicate with each other, and then the project manager will assign a task here to the engineer, and the engineer starts implementing this, a certain kind of file it has to do. And when the code does not execute, it will reiterate. If it executes, it will just append this code to the lists of artifacts, like the system design and the other files that might have been written. Okay, so here's our first jump to recurrent models. And because I find that very interesting, we know that context sizes are very limited for LLMs. And it may be a good idea to also be able to process longer text, longer contexts, for, let's say, summarization tasks, for instance. And the problem with standard LLMs and the transformer blocks is basically that in the naive approach, it has quadratic runtime. And as you increase the context size, things just get so much slower. But there are recurrent architectures which have some fixed size memory, like the recurrent networks you know maybe from the LSTMs, from Jürgen Schmidhuber, Sepp Hochreiter. So one of them, Sepp Hochreiter, is developing an architecture called XLSTM, and Google has this Griffin architecture. What we see now on the right side is a task for predicting the next token, or imagine it like being the next word. And you will see some kind of error rate. So with these recurrent architectures, they keep things in mind or forget them, keep others in mind to perform their tasks. And you can see in the curve in the lower one, the yellow one from Griffin, that a model that works on a context way longer than it has been trained for, it still performs very well there, while other models already get into making errors, not being able to predict anymore. And why is this important to us? Because it decreases compute, and you also need less data. It generalizes a bit better. So with 30% less data, you get the same accuracy and the same safety also. Well, another topic is multimodality. So we as people, we perceive with different senses. We can see, we can hear, there's tactile sensory. And also with models, we can have this functionality, and it might turn out to be quite useful, because let's imagine you're writing this computer game, designing some campfire, and you need the matching sound for it, for instance. Then, when you have embeddings that match, so that the sounds and the images produce similar kind of vectors, you can implement retrieval in the other domain, the audio domain, for instance. And also, you can perform some arithmetic in embedding space. So you might know it from autoencoders. When you take a person plus glasses, you get essentially me. Yes, and you can also do that across multiple modalities now, as you see with the bird and the waves, and you get the bird at the sea. Well, how does it work? There are different kinds of adaptation. If you want to adapt images to the text domain, you could say, I just caption this image without any prompt and see what the LLM does with the prompt and the image description. That might not turn out so well, because the description does not really match the user prompt. You can also use models that follow a prompt and output text. But more interesting is this last approach we have seen beforehand here with a single embedding space, so that you really get those same vectors. How do you do it? You have two types of encoder networks, one for the image, one for the audio. They are compatible, and when you put in compatible inputs and take a distance function on top of it, you want to minimize that distance, because it's more or less of the same. If you sample some things that are very dissimilar, you would expect a high distance. And so you can get this alignment. And you can not only get this across multiple modalities, but also across languages, for instance, to get better representations in your network. So one of the most interesting networks for us developers, at least, are the vision language models, because you can also do things like handwriting recognition and structured document extraction. So think of patient records where you need to extract certain information to be processed later in a statistical fashion that is actually robust. Or you could convert tables into SQL or HTML, which is processable very well. What you see here is the TNG AI assistant, and you see some payment transfer form. And with a proper prompt, you can get this form coded in a web framework like Angular or React. So that will really speed up our work, and we can focus on the creative parts, like sketching our system and get the blueprint done. Okay, so we also want to know how models work or how they think internally. That's a major area of concern, that models do some unwanted things. So we want to better understand it. From Anthropic, there's a paper, a publication called Towards Monosemanticity. And the interesting part is that they take the neural network. There are some activations in between, and they train something called a sparse autoencoder. Sparse means that you want to represent one concept in one dimension. So the opposite of that would be you've got a three-dimensional vector and 100 concepts in it. It's difficult to interpret. So we want to have one in one dimension. It's also very costly to train it. Josh Batson from Anthropic said even prohibitively costly, because you have to run data through the network and train this autoencoder. But later on, you can do great things. Like you could go back the way from a feature. If you take, for instance, sycophantic praise, then you clamp the values of the activations for that feature up. And when you input something like saying, stop and smell the roses, it will just be so over-exaggerating on things like brilliant, insightful, wisdom. So the model will behave totally different. And so you can use that to either detect things that are going on, like the model is trying to produce unwanted results, or you can clamp up some values. When you're thinking about creating code, there are different styles of codes. Let's say in scripting language, you can script without using type hints and with using type hints. If you find a feature in the model where you can clamp this up, you can customize the output, kind of. So that's a very mighty approach. Also, we have lots of data, and labeling is very, very expensive. So what we want is to learn a lot from unlabeled data, like we have it in pre-training of LLMs, and also in the image domain, where models become ever more powerful and see ever more data, we want to have some kind of pre-training. So the architecture here is joint embeddings predictive architecture. It's from Yann LeCun. That's the guy working at Meta, being head of AI there. And the basic idea in the image domain is that you have that you have some patches of the image. You give the model a context, and you have some targets you want to predict, because there might be spatial relationships within this image. So you encode this to an embedding domain. Let's think of vectors here. And you try to compute, to predict the target on the embedding space instead of on the actual image like you have done it before with the autoencoders. The nice thing about this is you need way less computing power. So the pre-training hours, you see, where is it? Here, yes. So there is less pre-training, and the quality of the models is actually even increasing. And that's great. Well, another domain of impact now is also robotics. So the current generation, you will see many types of robots being specialized, quadrupeds, or even robots like the stretch robot on the right that is just able to pick packages, to unload them, put them onto a conveyor belt. But most companies these days are striving for humanoid robots because you can operate them everywhere a human can operate. That's very powerful, but the current generation is, let's say, quite dumb. It does packing, sorting, moving, cleaning, and monitoring, like your hoovering robot at home. But the vision is to improve on this and to make them more and more useful. So what do you need for that? You need some kind of perception, like humans, and you need to be able to act somehow. So understanding language, for instance, is very important. So in the audio domain, we have models like Whisper 3 now. So whenever you input some audio sample or you have a user request, you can even change the languages in between. The system will understand you. It will transcribe it. Seeing improves vastly. And there are also improvements in hardware, from soft robotics to better sensors and cheaper sensors. And you need to combine all of this information also. So think of tactile sensors and sensory motor skills. When you pick some very delicate objects, you don't want to squash them. And the fun fact is, you can simulate that in environments that respect physics or are photorealistic. So the next generation of robotics is trained in simulators, because reward and reinforcement learning might be very sparse. You might need many, many samples until the system learns to perform a certain task. And the more realistic the environment is, then you have less transfer to the real-world domain. You see that with autonomous cars, for instance. The computer graphics are getting so photorealistic. If you have played recent games, you'll see that for yourself. And there are powerful simulators. NVIDIA is having this Isaac Labs for robots also to train. And in the beginning, you can do some imitation learning. So you have an expert, and you try to do the same thing. And later on, you can have sparse reward, so to say, less reward. OK, but things are really looking bright, but there are lots of unresolved issues. So the systems don't really generalize. A neural network is a function approximator. That means it learns in between to interpolate, not really to extrapolate. We might hit a boundary where this might not be true anymore, because systems are becoming so powerful that they can reflect on their results. Like nowadays, LLMs are being used to filter out web content that does not meet educational quality standards. The system does not need to be perfect, but filtering out means you have higher quality data and discard the other one. Autonomous learning is also very difficult because there's an effect called catastrophic forgetting. If you learn and learn new stuff and forget to train on what you already know, you might forget things. And this happens with stochastic gradient descent. Hallucinations and misdetections are also a common case. So current models might not yet have reached the threshold to be useful in every domain. But it's coming in the future. Also, high-quality datasets play a role. It's very easy to scrape the web, but there's certain kind of data you cannot get anymore from the web, like thoughts of professional software developers. If you have requirements documents and need to create some diagrams, you have to think of which kinds of diagrams and how to reduce information. You cannot really scrape that from the web, so professionals have to create this kind of data. Also, lawyers do have to create it. And that will be taking some time, I would say. Also, the network architecture of the future is very unclear. So what we have seen now is these transformers. They enable us pre-training. You have seen GPT-4o, Claude 3.5 Sonnet. But when we want to get to higher quality, it might need some more foundational research until we get there. And the architecture from the future could look more like recurrent architecture that is able to stream, maybe is able to plan a bit, has some memory built into the model so that you don't have to create so complicated agents anymore. And we need some explainability and interpretability. Some more of it. But yeah, quality improvements, arrive. So pre-pandemic, you will see here on a very boring task of object detection that there's a certain score, and this score has really increased these days. Interestingly, also using vision transformers. So transformer architecture also has its impact on the vision domain, not only on text. And what I want to say is, even your boring use cases and POCs that did not work out yesterday or 4 years ago, they could as well work today. And there's even room for improvement. So let's have a look at an example. Here we see an image segmentation. You might have seen that where you can just have a model that has a certain fixed size of classes, like cats and dogs, or even 1,000 classes, like an ImageNet in the dataset. That's very restricted, because you've only got this fixed size of classes. And nowadays, you've got OpenZ detection and also segmentation, which means drawing pixel masks. OpenZ means you can just train on more data and accommodate for a variety of classes. And the model also learns some sense of objectness, so it can handle unknowns as well. And the other interesting part is in segmentation, previously you would just have gotten some kind of dog. Now you can give points that lie within and some points that lie without. So I've taken the tongue with us and excluded the body, for instance. That was not able. We were not able to do that previously. Also, you can just input prompts of a category, like segment the animal or segment the dog. Well, that brings us to the business potential. And the section is meant for inspiration. So we will jump between different domains. And you can just think about how you could apply that to your use cases. So in health case, one very interesting thing that's happened is AlphaFold 3, because it can predict the structure of proteins. Proteins are those molecular machines that can do lots of tasks. There are enzymes that speed up things. There are transport mechanisms. Some give us cell structure. And you can even cure diseases. Because when you've got a certain kind of disease, you need a protein to dock onto the virus and destroy it. And if you can predict how this protein looks, you can design one that cures your disease, in fact. But also, do not forget about medical imaging. As we have seen, also computer vision is constantly improving. Well, in finance, everything's about seeking alpha, outperforming the market. And you need to do many things if you want to achieve that. Some people even say it's not possible to beat the market. But if you want to do it, you need to predict some things like market trends, even company success. You need to extract information from various sources. Those might be earnings calls. Earnings calls are audio. So a model like Whisper helps you in transcribing. And then you could use an LLM to extract some information, some factual basis where you perform some statistics on top. And you can also derive sentiment if you're into that domain. Well, also anomaly detection is constantly improving. So when you have a set of financial records, you also want to see whether there are some fraudulent activities going on. What you could not process until now are the descriptions of the bookings. So in fact, at TNG, we are also doing that. We validate what people write on their timesheet, because some people get frustrated and they might write things like, oh, this damn configuration did not work, 1 hour. So we don't want to put that on the bill, right? Well, manufacturing is very interesting because it combines this robotic process automation with computer vision and quality control. So there are many things to explore there. Also digital twins. It's a very nice thing when you have a simulator that behaves like your factory, because you can train your robots on that factory. You can even train collaborative agents that will create a whole product. So that's very promising in my point of view. Well, retail is a very visual thing. So there are things like visual try-on and shop the look. So manufacturers of luxury watches like Baume & Mercier are creating apps now where you can see how it looks on you. L'Oreal has this cosmetics thing where you can develop your own style before you buy the products, which is great because you don't have to spend money on the wrong products and can buy the right ones. Also on the right side, you see some image from Walmart. That's virtual try-on. The interesting part about this is that you get some kind of body mesh and you have some key points. And then you can map the clothes onto the body and it looks really natural, which is just great for developing your own style. Okay, so also in transport and logistics, there are many influences, like 5G. Within Germany, you might even have round-trip times of 20 milliseconds for communication. So even if your autonomous vehicles, like trucks, do not operate fully autonomous, you can have teleoperators. So whenever the truck encounters some roadblock, you might bring it on track again, and it can be autonomous for the rest of the time. So you can save a lot of money. Also, many people say, fully self-driving from Tesla, that hasn't worked out so well. Things are taking their time, but you have also to accommodate that the computational power in the cars nowadays is not that much. And models being smaller and having less compute, they're not that accurate. So a Tesla of the older generation might only have 50 TOPS of computing power. And now you see there's the jump of Drive Thor from NVIDIA, which will arrive in 2025, hopefully, that has 1,000 tera operations in floating point space. That means you don't have this break from the floating point values to integers anymore. And that could enable us to run models that are much more powerful and bring us nearer to the autonomy there. Also, quantum AI may play a role in things like route planning, because you've considered so many options. But here we've got the problem that we've got too few qubits and too many errors. So we need to simulate a lot to reach a conclusion. But the traditional solvers, they are still faster these days. But that might change in the future. Also in education, now is the time to develop interactive tutoring systems. So systems that help your children solve their homework. Not having it done by the machine, but helping them to understand their faults, their errors. So Duolingo, for instance, where you learn your languages, they are employing those systems right now. They can say what you did wrong, why you did it wrong. They can create tailored conversations for you, where you have just those examples where you don't excel at currently. And there it is also important to have vision, to see like things that your children wrote out on their homework sheets, audio to prompt it via text, and get some audio output. So if your child is, for instance, not able to read yet, a system that understands and is able to synthesize speech comes in quite handy. Okay, so for a living, we don't have to do work anymore, probably in the future. John Deere, for instance, is working on autonomous tractors. So the interesting part here is that the weeding process of finding the things you want to remove works pretty well with computer vision, so you can do it very fine-grained. And also, when you can precisely monitor the soil, you can apply irrigation, save water, and apply fertilizer in a way better way to use less. Okay, and entertainment. You might have seen this, maybe in our showcases. We've got some karaoke system where you can generate your music, get the audio track and the instruments separated, and then have your karaoke. That's possible these days. There's video generation where you might have heard other talks. And from my point of view, in computer games, things will get very interesting because you could have naturally flowing dialogue systems if they don't go off the rails, of course. So you have to constrain them a bit. And there's procedural generation. Content generation does not always mean generative AI as you have seen it with diffusion processes. It can also mean that you develop systems that are a bit more rule-based. So the Unreal Engine is a good example. If you buy something from the asset store these days, you put it into your landscape and it will change the surrounding accordingly that it really looks natural. Well, one other domain that's very interesting is the legal domain. Documents are so difficult to understand. You need to take care of the presence or absence of certain clauses. You need to find them. You need to assess risk in your documents that you sign. And maybe in legal cases, you also want to predict the outcome. If you will have success or if it's highly unlikely to succeed, then you can save the money. And also, laws change. especially as with the generative AI, you have seen the AI Act. And those changes are advertised, but as a lawyer, you need to monitor those changes, and you might need some kind of summary on how that affects your ongoing cases and the future ones. You could have an agent that does this research and summarization for you and tries to read through your cases. Well, let's think a bit more broadly now about business processes. Please be careful. The AI Act states that certain applications are high risk. Why are they doing this? They want to protect the individual against bias and discrimination, which is very important, because systems that are trained just on the web, they might have some biases. They might be latently racist, for instance. And when you're doing resume screening, for instance, this is high risk, because you're relying on a system that you don't fully understand and derive some results. Even if you say a human is going to review this, that's not enough, because you might already have the prejudice in mind. So recruiting is very sensitive. But in marketing, you could do targeted recommendations, find out which products fit well onto people. You can analyze all the sentiment, how people think of your company, what you should improve, what you should keep on doing. So that can help you in that case. Okay, so that was a lot of stuff. Let's try to look into the crystal ball, what the future might bring. So the bright future is that data sets evolve, the systems get better and better, foundational research has breakthroughs. There are more and more APIs being open. Like we have Deskly at TNG, where we book our desks, but they don't have a public API yet. So that will all evolve. The agents will be able to use more and more tools, will feel well with calling public APIs on your behalf. And the semi-autonomous agents that have to get your feedback all the time will evolve into more fully autonomous agents. But what you want in the end is still to confirm that you want to buy something. So it should still give you some options, like buy this flight or the other one, and you just confirm. So you don't have to do that much of work anymore. You can focus on the creative parts, focus on, for software developers, for instance, on architecture, and be driven by interest. But that sounds too good to be true, and I'm a bad person. I won't leave you with that feeling. There are delaying factors. Of course, energy is limited. It takes time to produce more energy, so this will delay us a bit. Compute is also limited, so capacities at TSMC, for instance, or Samsung, they are just sold out. So it takes some time for the elasticity to grow there. Also, the foundational research might take some years to find the better architectures. And regulation will kick in. So you have to take care of which kind of data you gather. Data gets more expensive, so we might arrive at an oligopoly where only companies like Microsoft, OpenAI, Google, Amazon are able to stem this financially because it's so costly. And when most of the content will be generated by AI, it might be generated by today's AI, which has not that high of quality, so you cannot train on that anymore. You need to create and curate your own high-quality data sets. And of course, there's the matter of geopolitical instability. Whenever there's some hiccup, it could get really nasty with chip production. Well, so what should you take away for today? Basically, there are hot topics in research, like agents, multi-agents, foundational models. We have simulation platforms to train things on. We've got this robotic stuff. And you should reevaluate your POCs, of course, because it might just work today. And also AI developments might have reached some plateau. If big companies are gathering more high-quality data you cannot scrape from the web right now, it will take some time until we get the next generation of models. Thank you very much for listening.
So thank you very much for this talk. And we now still have a bit of time to accept questions from the audience.
Just a really quick question. First, thanks for the talk. You mentioned simulated environments, especially for reinforcement learning. Now, I can imagine that a car trained on a photorealistic environment is a lot more expensive especially in terms of compute and power to train. Is there like a rule of thumb at which point it doesn't make any sense to use a complex environment because it just adds so much more cost to the training process? Or is there like, it just depends on the use case?
Okay, so thank you for the question. There are different approaches. So one of them to tackle the complexity is to detect certain things upfront and also derive some rules or train a system on top of that. But people in research have found out that end-to-end models, they can better handle all these corner cases, maybe even. So that's one of the things where you might want to do this. And we are getting this more compute so that it will just be, we will be able to do this, and have the better results by end-to-end learning. This kind of the holy grail.
Thanks for the talk. Regarding explainability, you mentioned the idea or goal that you try to have a human concept represented by a single dimension or a single vector. Mm-hmm. Is that easy to achieve, and do you have to make some compromises regarding the overall quality of the output?
Yes. So it's not easy to achieve, as you have to put in a lot of compute. You need to run data through the LLM up to that stage where you're going into the activations and train your autoencoder. So that's just quite costly. And the concepts might not be concepts that a human understands. Psychophantic praise is easy, but writing styles, for instance, they can be more complex. So you can only visualize and try to grasp what the system has learned and to influence it. But if you influence it too much, it might even identify with concepts, like the Golden Gate Bridge. If you clamp that feature up, the model will once say, I am the Golden Gate Bridge, and does not even answer your question anymore. So results can also degrade, that's true.
I say thank you very much to Mathias. Let's give him one more round of applause, and then we have half an hour of break.